I'm deathly ill, so I won't have as much energy as usual today. This week, the rest of this week anyway, we're talking about efficiency. And this is really the only week in the course that we're going to make a big deal about efficiency. And the reason for that is, in the first course, we figure it's much easier to speed up a working program than to debug a fast but wrong program. So our emphasis is on getting you to write programs that work altogether. And next semester in 61B, they'll start doing in earnest the things that we're just dipping our toes in this week. But we want you to understand what they're talking about when you get there. So here goes. I have up on the screen a rather trivial program that you've seen before that takes a sentence of numbers and returns a sentence of the squares of those numbers. And it does this by taking square of the first number and a recursive call to squares for the but first. So I want to ask the question, how efficient is this? And the question comes up, how should we, oh no, wait, before I do that, let me do administrative things. Sorry. Go to section this week, for sure, and get your TA to put you in a group of 4. Get to know your group of 4, start studying together. You're going to work together on the midterm, and you're also going to work together on the later projects in pairs. So get to know each other. All right, I'll tell you about midterm 1, which is coming up in the week after next. The reason we have a lot of midterms, my mom always complains about this. She says we shouldn't call them midterms if there's more than one of them. We should call them quarter terms or something. The reason we have a lot of them is students like it that way. Whenever we try to back off, students complain because this way, one problem is not worth too many points. You know, if you mess up one problem, you haven't killed yourself, you know. So students like it. And also, the week after next is drop deadline. So by Friday of the week after next, you will know how you did on the midterm, and that will help you decide if you're staying here or not, which I hope you all are. So in the midterm, what's going to happen is you'll do 5 or 6 or so questions. You'll do it individually. You'll hand them in. And then you will do 1 or 2 of the same questions again in a group. And in the unlikely case that your individual score is better than your group score, we'll use your individual score, but otherwise we compute a weighted sum. You'll see the exact details after we know the exact details because it depends which questions, you know, how many points are involved. We compute a weighted sum that still adds up to 40 points maximum, and that's your grade. And typically it actually improves people's grades by a point or 2, but more to the point, the reason we do it is it's a way of getting you to learn things very quickly. You know, things that you've been sort of unclear about, you will understand those questions by the time you leave the exam. So it's really a good experience. And you'll also find that it's much more enjoyable doing a group exam than an individual exam. So it's fun to watch too for us. Okay. Some people did not turn in their homework 1 in the homework box, including one person who put it in my mailbox. That's the wrong thing. And other people who didn't turn it in on paper at all. If you didn't turn it in the homework box, as a consequence of that, there is no reader grading your assignments. And as a consequence of that, you're never going to get any grades for anything. So to fix that, somebody has a hand up, but maybe I'm going to answer your question. To fix that, what you need to do is send an email to the reader to whom you should have turned in homework 1 and say, I'm sorry I missed turning in homework 1 on paper, but I exist, please add me to your list. Does that answer your question? Okay, go ahead. Yeah, if you got your paper back, then it was probably graded. But the other thing to do is run the shell command glookup. At the shell prompt, you say glookup, all one word. And it will tell you all of your grades that have been posted. It's a little early for this, but if you have missing grades or grades that you disagree with, there's an official complaint mechanism on the course webpage. There's a link to grading complaints. Click here. And that will allow you to enter a grading complaint. Later on, we're going to have grading complaint deadlines so that I don't hear about your missing homework 2 grade after the final exam, because you're 1 point short of something. By then, all the readers are off skiing, or let's see, this is spring semester. The readers are all off surfing, and it's way too late to start dealing with early complaints. So there are going to be deadlines for filing complaints that'll come up in a bit. But the main thing is to make sure that some reader knows about you from the beginning. The Computer Science Undergraduate Association is having a general meeting. That means a fun get-together this Friday, 6 p.m. in the Wozniak Lounge, which is on the 4th floor of SOTA, for something or other. But there are a lot of signs about Wozniak Lounge this way. You can't miss it. And they're playing video games and boring things like that. So you should come. I'm asked to tell you that there's a decal class. For those who are new here, decals are courses run by students, typically pass, no pass, rather than letter grade. And some students for quite a while have been running a decal class on how to be a Unix system administrator. And if you're interested in that, decal.org/sysadmin is how to get more information. By the way, also, I should say, every week, 3 people ask me, can I announce such and such in your class? And it didn't used to be so many, and so I used to say yes to everybody. But now it's gotten so heavy that I say no to people who aren't really directly computer science related. So these are, so they win. Okay, now, how do we think about the efficiency of this squares program? And the most obvious way is to just, look at your watch, hit return, and see how long it takes to finish. But that isn't a very good way for a bunch of reasons. One of which is you're not just measuring your program, because on your computer, even though you're the only human being using it, there are anything from 40 to 100 other processes running, typically, depending on which operating system you have. And they take up time in sort of irregular bursts. So if you do the same timing experiment twice, you'll probably get 2 different answers. You, of course, can't really do it with your watch because the precision isn't good enough unless we're taking the square of 3 million numbers or something. But you could ask the computer to time, how many millionths of a second did it take to do this. But it wouldn't tell you anything very interesting, also because besides measuring the efficiency of your program, you're also measuring how recently you bought your computer, right? Because computers run at different speeds, and that has nothing to do with this algorithm. So we'd like to find another way to talk about the efficiency of algorithms. And the way is to talk about how many basic operations does it do. And a basic operation is something that the computer can do in a constant amount of time, regardless of what the arguments are or anything. So we take the arithmetic operators to be basic, and if, and cons, and so on. Now you haven't done cons yet. First, sentence, but first, those things. Some of these I'm hand-waving about. Actually, most of them I'm hand-waving about, because if you deal with big enough numbers, then the time it takes to add them starts depending on the size of the number a little bit. But we're not going to get to numbers that big. We're talking about numbers bigger than a couple of billion. The arithmetic slows down a little depending on the size. But for our purposes, adding two numbers takes a constant amount of time. First and but first take a constant amount of time. We're going to learn, excuse me, we're going to learn next week that that's not true about last and but last. And you'll see why. But for now, just take my word for it. First and but first are fast, constant time operations. Sentence, in general, is not a constant time operation, but it so happens that in this program, the first argument to sentence is a single word, and the second argument is a sentence. And that combination happens in constant time. That's a very fast thing to do. So all of those things we're going to take as constant time operations. Empty question mark, constant time. So each recursive call to squares does 1, 2, 3, 4, 5 constant time operations, plus the call to square, which is itself constant time because all it does is a single multiplication. So that's a total of 4, 5, 6 constant time operations per recursive call to squares. How many recursive call to squares are there? Well, there's one for each number in the sentence, basically. Plus one because there's the empty list. But that's not so important. What's important is if you have twice as many numbers, you do twice as many constant time operations. And so the amount of time taken by this program is proportional to the size of its input. Okay, questions about that? That's got to be clear to everybody, or else we're going to be in trouble later this afternoon. Okay, so you call squares. I called squares with a sentence of 5 numbers. It goes through, it does a bunch of things to the number 5, which is the first one, and then it calls squares of but first of sent, which is a recursive call to squares with 4 numbers, and so on. So there's a total of 6 calls to squares, counting the first one and the last one. And each of those takes constant time plus however long the rest of it takes. So it's constant time times n. So it's proportional to n, the amount of time. Okay? So what we're going to say, they finally fixed this board. Thank you very much. So the time is proportional to the size of the input, the number of numbers. Okay? Let me make this a lowercase n because otherwise you're going to get confused later. Okay. We're going to write that as saying that the time is theta of n. That basically just means is proportional to n, but in a little bit I'll talk about the precise mathematical definition, which you can see over there is a little bit longer. And you'll see why when I get there. Okay, next example. Oops. Is sort. Sort's a bunch of numbers. So if I give it the same numbers, I should get back a sentence of the same numbers but in increasing numeric order. Okay? Now, there are many different ways of writing a sort program. This one that you're looking at is not the most efficient possible. Although it's actually pretty good if you're dealing with 5 numbers like this. For a small number of numbers, it's fine. But not for bigger numbers of numbers. But we'll see when we do the excuse me, the analysis of its running time, why that is. So this algorithm is called insertion sort, and it's what you do when you pick up a hand of cards. You're playing poker or bridge or whatever it is. There's a pile of cards that have been dealt in front of you. You pick them up, and I'm left-handed, so they're in my left hand. And then one at a time, I stick the card somewhere in my right hand, depending on where that card belongs in order. That's an insertion sort. And the way it works is, well, if the sentence is empty, then return the empty sentence. That's the base case. Otherwise, we pull out one card, and that's the one that we're going to insert last. We recursively sort the rest of the hand. So that's n-1 cards. We get into order somehow. And now what we have is a bunch of cards that are in the order we want them, a bunch of numbers in this case, that are in increasing order. And we have one more number that we want to stick in where it belongs. And that's the job of insert. Okay, and you have to first understand that if in fact the recursive call to sort works, then the big call to sort works, because it sorts all but one of the numbers, and then it puts that number where it belongs. So let's look at insert and see how that works down here. It's a cond because there are three possibilities. The first possibility is for the very first card that I picked up and I'm trying to insert into my hand that's empty, and I just stick it in. So if sent, which is the already sorted rest of the hand, is empty, then I return a sentence containing just one card. I call sentence because I always want to return a sentence. The range of this procedure is sentences. So I'm going to have a sentence of length 1 containing my card. If there are already some cards in my hand, then what I do is compare the new one with the smallest, in this case number, the smallest number. So compare the new number that I'm trying to insert with the smallest number I already have, which is the first number I already have, because in the call to insert, sent has already been sorted. So when we call insert, we're promising to give it an already sorted sentence sent. And now I want to insert num there, and I'm asking the question, is num smaller than the very smallest number, namely the first number, in sent? And if so, I just stick the new card in the front, which is what that call to sentence does on this line. Sentence num sent. So I stick the new number in front of the old numbers, because if it's smaller than the first old number, it's smaller than all of them, since the old ones are already sorted. Okay? Otherwise, if the number is bigger than the first number of this already sorted hand, then what should be the first number of the result? It shouldn't be the new number. It should be first of sent, which is the smallest of the old numbers, and we've just decided it's smaller than this new number. So we're going to combine with sentence first of sent and a recursive call to insert this new card into the rest of the hand somewhere. So in effect, what we're doing is moving through the hand left to right, saying, is it bigger than this? 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 Here's one that it's smaller than. Stick it in there. That's what this is doing. Any questions about how insert works or how sort works? Okay, this ought to be easy. I hope actually that most of you have seen this before in some previous class somewhere, doing an insertion sort. So, how long does it take? Well, obviously, in order to time sort, we have to time insert. So how long does it take to insert something into a hand of length n? Well, it depends, doesn't it, on how big the new number is. Right? So the best time, we only do one comparison. Everything else is a constant time operation. So it takes constant amount of time, regardless of the length of n, because we don't have to look at all the rest of the numbers. We see that the number is smaller than the first number, we're finished. The worst time is the new number is bigger than all the numbers we already have. So we go through the whole thing, boom, 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 finally discovering that it's bigger than the last one, and then we're in the base case where we have an empty sentence to deal with, and there we are. So that, that takes an amount of time proportional to n. So on average, if the numbers are coming in randomly, we don't know any patterns of the numbers, we will expect to have to look at half of the numbers. But remember, constant factors don't matter, we just said. If the program takes twice as long or half as long, it doesn't matter. If it takes twice as long, just wait a year, buy a new computer, and it'll take the same amount of time. So constant factors don't matter. So theta of n over 2 is really the same as theta of n. We don't usually ask the question, what's the best time? We ask either what's the worst time or what's the average time. Those are the things people want to know because, you know, they have to be realistic in making plans for how to use their computers. Okay, so what about sort? Well, sort calls insert n times. The other things it does are constant time operations. It calls sentence and first and so on. No, it doesn't call sentence. It calls first, but first, empty question mark, and if. Itself recursively, and then insert. So all of those are constant time, except for the call to itself, which we deal with by multiplying the time for one thing by n, because we're making n recursive, because the recursive calls are just but firsting their way through the sentence. We're going to look at every single number in the sentence, so there are going to be n of those recursive calls. How long does each one take? Well, theta of n in either average or worst case. I'm lying a little bit. Why? Uh-oh. Nobody gets it. Yeah. No, but first does take constant time. I'm not lying about that. It's not the constant time operations I'm lying about. It's the mathematics. No, if there's a constant number of the constant time operators, because it's a fixed length program. So that's all constant time, yeah. If the numbers get really big, then the comparisons will take longer. That's true, but it's not the one I meant. Okay, I'll tell you. It's not really true that each one takes theta n. The first one does at most one comparison. The second one does at most two comparisons. Third one, three. So what we're getting is not really time n times n. What we're really getting is 1 plus 2 plus 3 plus 4 plus n. That's how much time it takes. So it's this many comparisons that we're doing. But as I hope you learned in high school, the sum of the first n integers is n times n plus 1 divided by 2, which is n squared over 2 plus n over 2, which is theta of n squared. So it comes out theta of n squared the simple way. We just theta of n multiplied by n. And it also comes out theta of n, except half as big because of that over 2 thing. Another way to think about that, if you didn't learn this in high school, is on average, what's the biggest number of comparisons we do to insert a card? On average, it's the n over 2th card that we're inserting. So it takes time n over 2. So it's basically n times n over 2. So that's pretty close. All right. I would like you to be able to recognize both of these patterns because they're very, very common, and you should be able to see their order of growth in a second. You should say, oh, this is going through a sequence doing some fixed thing for each element of the sequence. Theta n. Oh, this is going through a sequence doing a theta n thing for each element. Theta n squared. Okay? So those are the easy cases. Time out. Hello? There we go. So those of you in the front row are probably going to get sick next week. Anyway. Okay. Now let me talk about the real serious definition of theta n. Because there are a couple of things in it that may be of interest. It says, a function f, well, first of all, before I can define theta, I have to define big O. That's called big O, as in capital O. It's not a 0, it's capital O. F is in big O of G, if and only if this is true. What does this say? This says there exist two numbers n and k such that for all x greater than n, absolute value of f of x is less than or equal to k times the absolute value of g of x. So first thing when you see that formula is for our purposes in analysis of algorithms, you can forget about those absolute value signs. Because the functions f and g are how long it takes for some program to do something. Those numbers are always positive. So far, nobody's invented any algorithms that work in negative time. So we don't have to worry about the absolute value. We do have to worry about the purpose of n and k. Let me start with k. K is the one that says we don't care about constant factors. If one program takes time 3n squared, and another program takes time 7n squared, those are the same, unless you're a video game developer. If you're a video game developer, then you're really, really, really pushing the state of the art of the hardware. You're driving it as hard as you can. Every cycle counts, and you have to worry a lot harder about constant factors. But for the rest of us, you don't like the constant factor, wait a year, buy a new computer, fixed. And it's important because it's not that I'm telling you to be lazy. It's that I'm telling you when you're trying to make your program faster, the place to put your effort and your time, because your time costs something too, is in trying to improve the order of growth, not trying to improve the constant factors. And we'll see a great example of that coming up in a bit. So that's K. So F is in O of G, even if F is 3 times as much as G. It means that F is bounded by some constant times G. The functions that we're interested in, the g functions, are things like n and n squared. That is to say, when I say n as a function, I really mean, of course, n maps to n, or n maps to n squared. So take these things as representing functions. Or x squared. Here the variable is x. Doesn't matter. So we're interested in sort of big families of functions, like all the quadratic formulas. That's a family of functions, and they're all within a constant factor of each other. So if we say that something is the order of growth of n squared, we know pretty well that it's, what its bounds are. So k lets us ignore constant factors. What about n? N lets us ignore small values of x. The reason that matters is sometimes you run an algorithm that has a large constant setup time. So here's the size n, here's the amount of time it takes, and it does something like this. It doesn't start at 0. Okay? Well, how does that compare to n? F of x equals x. That's down here. This is bigger than that. But how about, is it bigger than 2 times that? Well, it is for a while. But eventually, f of x equals 2x overtakes f of x equals x plus a big constant. Okay? So what we're saying is, never mind this stuff that seems to be out of bounds. Why is it okay for us to say that? Why is it okay for us to ignore small values of x? Somebody. Yeah. On large things. Yeah, because if x is small, remember these functions we're looking at are how long does it take to solve the problem if you have an input of size x? Well, if x is small, the amount of time is going to be some number of milliseconds or something. So who cares whether it's 1 millisecond or 999 milliseconds? It's still not worth thinking about. The cases that matter are the cases where x is large. So for large x, we can ignore setup times. And that's what that n is in the formula. So the formula says, ignoring small values of x, f is bounded by some constant multiple of g. One function is theta of another function if and only if f is O of g and g is O of x. Well, how is that possible without them being exactly the same function? It's possible because of this constant factor. So think about, to take an easy case, the functions f of x equals x squared, and g of x equals 3x squared. Well, f of x is x squared is certainly O of 3x squared. It's bounded by 3x squared all the time. But g is bigger than f, but only by a constant factor. So if we pick k equal to 3, then we have g being O of f. So x squared and 3x squared are the same order of growth. It's going to turn out that any quadratic function, not just ones that are a multiple of x squared, if you have like f of x equals 4x squared plus 100x plus 9. Okay? Well, for x greater than 100, x squared is bigger than 100x, right? So I'm going to say n equals 100. I'm ignoring everything less than 100. All right? So this is less than x squared. And for x greater than 100, 9 is less than x squared. Right? So I'm going to take k equal to 6, and that gives me 4x squared plus x squared plus x squared, which is bigger than f. Okay? So f of x is bounded by 6x squared. G of x equals 6x squared. Right? And so any quadratic function is the same as any other quadratic function to within a constant factor. And the same is true for any power of the argument. Okay. So that's the formula. By the way, you will very often see in the literature this notation, f equals theta of g. If you think about it, that doesn't make sense. F is a function. Theta of g isn't a function. It's a family of functions. They can't be equal. So the really right way to say it is that f is an element of big O of g, or f is an element of theta of g. Okay, so that's the right thing. But you will see the other thing in books, so don't let it throw you. This is what they mean. All right. For our next step, John Bentley worked at Bell Labs anyway at the time. I don't know what happened to him since. Wrote a great book called Programming Pearls, which is about how to understand what you're doing before you start writing your program by looking at examples. And in the book, he talks about this order of growth business. And to make the point that constant factors don't matter, he wrote 2 different programs to solve the same problem, but using different algorithms. And the one on the left is theta of n cubed. The one on the right is theta of n. So we would expect the n cubed one to take longer than the n one. But in order to get the huge constant factor, he ran the first one on a Cray 1 supercomputer, at that time the fastest computer in the world, in compiled, highly optimized Fortran, which is what supercomputers do. And the other function, he wrote in BASIC on a Radio Shack TRS-80. I don't know if any of you are old enough to remember those things. It was, a machine about like the Apple II or the Atari 800, is, a little 8-bit toy computer. And he ran it in interpreted BASIC. So it's really, really, really slow. So the constant factor is 19 million to 3 in microseconds or something. Yeah, microseconds. That's what it was. 19 million microseconds is the constant factor. So he runs this for various values of n. And at first, the fact that we're running on the supercomputer does way better than the little toy Trash 80 from Radio Shack. Namely, for n equals 10, it takes 3 microseconds on the Cray, and it takes 200 milliseconds on the TRS-80. So that's a huge difference. That's, a factor of 100,000, almost. For n equals 100, it's 3 milliseconds versus 2 seconds. So milliseconds, we're still doing 1,000 times better at n equals 100, but the slow one is only taking 2 seconds. It's a blink of an eye. For n equals 1,000, the Cray takes 3 seconds. The TRS-80 takes 20 seconds. So the Cray is still winning, but not by very much. Right? We're now down to a factor of 7. And the amount of time is still, it's not the blink of an eye anymore. It's 20 seconds, but it's pretty slow. It's pretty fast, You wouldn't complain if it takes your computer 20 seconds to do some big calculation. Maybe you would, but I wouldn't. Okay? At n equals 10,000, now the TRS-80 is winning. 10,000 is still a pretty small number. Small enough so that we're talking about minutes of computation, not hours or days or anything. Minutes of computation. The Cray takes 49 minutes. That's almost an hour. The TRS-80 takes 3 minutes. Way better. Because n beats n cubed, regardless of the constant factor, once n gets big enough. 100,000. He didn't actually run it on the Cray because he couldn't arrange to get the machine to himself for an entire month. He just computed how long it would have taken if he had done that. And the TRS-80 is taking half an hour, so that's a significant amount of time. But it's not an impossible amount of time. And already we're dealing with 100,000. That's, for example, more than there are Berkeley students. So if we had a database of all of you, we'd be faster than this. At n equals 1,000,000, the TRS-80 took 5.5 hours to finish. So that's quite a long time. But if he had actually run it on the Cray, it would have taken a century. Okay? So the point of all this is to persuade you that it's really true that constant factors don't matter. By the time you're dealing with any significant amount of time, more than minutes, constant factors really don't matter compared to orders of growth. All right, one last thing on this topic, and then we're finished for the day. And that's this table of what the orders of growth are for solving different kinds of problems. And you don't have to try to memorize this. I'm not going to ask you to regurgitate it on a test or anything. But it really is a good idea for you to get to be sort of have an instinctive feel for these different families of times. So the first one, it's f of n equals 1 through f of n equals n, is times for search algorithms. So linear time, the family theta of n, is searching in the most straightforward, idiotic possible way, sort of butt-firsting your way down a sentence until you find the thing you're looking for. And that's fine if your sentence is of length 10. But if you want to look up a number in the phone book, you don't do it that way, right? You don't start at the beginning and say, well, is it Mr. Aardvark? No. Is it Mr. Abalone? No. Because you'd never get to your friend, xylophone. Instead, you do something smart, like you say, oh, my friend xylophone is going to be most of the way through the book, so let me just open it 9/10 of the way through. And then you start flipping pages back and forth. Well, the computer equivalent of that is to cut your data set in half, so you sort it, first of all, has to be in order. Then you look at the one in the middle, say, is the thing I'm looking for bigger or smaller than that? And you cut off half the data each time. And that takes time proportional to the log of n, which is way, way smaller than n for significant n. If you're really, really smart, you invent a data structure called a hash table, which you'll use in 61B. And that allows you to do searching in constant time. No matter how many elements are in the table, theta of 1 time to find things. So that's how the big boys do it. So that whole thing, everything from 1 to n, those are searching and problems that are like searching, where you're going through looking for one thing or doing something to each one, or that kind of problem. The next family, the paradigmatic example, is sorting. Insertion sort, which we looked at, you'll recall, was theta of n squared. If you sit down right now, if you haven't taken a data structures class, if you sit down right now and invent a sorting algorithm, it will be theta of n squared. Because basically what you're going to end up doing, more or less, is comparing every number to every other number. And they're n squared such comparisons. But if you do take a data structures class, or you're really clever, and think about it for quite a while, you will invent a better sorting algorithm that takes time n log n. N log n, it turns out, we can prove, is the best you can do at sorting by comparisons, by comparing one element with another. It is n log n comparisons. In special cases, we can do better than that. For instance, let's say I have a bunch of junk mail that I'm sending to the city of Berkeley, to every resident of the city of Berkeley. And the post office requires me to sort them by zip code. Okay? I don't have to sort them by what street they're on. I have to sort them by zip code. Well, there are about 10 zip codes in the city of Berkeley. So all I do is I put 10 buckets on the floor, and as I just look at each letter and toss it into the right bucket. And that takes theta n time. So where the number of buckets is small compared to the number of things you're looking at, then you can do better than n log n time. But in the ordinary case, you can't. So that's sorting is the next big category. And by the way, there are many, many problems that are like that, where the straightforward way to do it is to compare every element of some set with every other element of the same set. Whenever you find yourself in that situation, this is a little nugget of advice for later life. Whenever you find yourself writing an algorithm that's theta of n squared, stop and ask yourself, what if I sort the data? Will that make it faster? Because you can do the sort in n log n. And sometimes dealing with sorted data, you can now solve your original problem in linear time, in theta n time. So if you remember that sorting can be done in n log n, that can be really useful in speeding things up. After that, the polynomial functions get pretty sparse. There are a few graph algorithms that are theta of n cubed. The canonical thing is matrix multiplying two n by n matrices. So if you remember how to do that, there's n squared numbers in the result. Each of those n squared numbers is the result of multiplying n pairs of numbers, a number from here and a number from there. Boom, 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 boom. So that's n cubed multiplies. Somebody got a PhD thesis a decade or so ago for discovering an algorithm that could do it in theta of n to the 2.8 something. Nobody uses this algorithm because it's way too complicated. It's just hard to program and get right. But it can, in principle, be done. It's slightly better than n cubed time. And that's the best we can do, we think. And then, as I say, there are a few problems that have bigger polynomial times. But for the problems that really come up, we then take a huge jump to exponential time, to things that take time 2 to the nth power. Those are the ones where you have to look at every possible ordering of the n things. Like the canonical example is, I want to visit n cities, and I want to spend the least amount of time on the road, and the cities are geographically sort of all over the place. In what order should I visit those cities to take the least amount of time? That's a theta of n squared problem, because as far as we know, the only way to do it is to enumerate all of the 2 to the n orderings, and then, all the n factorial orderings, even worse, n factorial time, and then take that. So 2 to the n factorial, n to the n. These are called intractable problems. Intractable meaning, although it's theoretically possible to do it on a computer, in practice, it's not possible. Because for any interesting n, like n equals 20, it would take, the entire length of the universe from here on out to do it. So instead what they have to do is say, well, I can't find the very best solution, but let me look for algorithms that'll get a guaranteed pretty good solution. And there's been a lot of progress on things like that. Okay, more next time.